Hey everyone, welcome to our video today on infrared spectroscopy or IR spec. We'll be going over the concept of IR spectroscopy today, talking about the different zones of the IR spectrum and highlighting really what this spectroscopy process is about, which is really about understanding what functional groups compose the molecular structure of the molecule that we're looking at. So I'm going to start by going over the concept of IR spectroscopy, and spectroscopy overall has to do with photons interacting with matter. So when you have something like a molecule, like this one, you see that there's some bonds here connecting the atoms. And what happens is when a photon comes in and strikes this molecule, this causes a vibrational energy. A lot of molecular vibrations kind of occur between these atoms, causing the bond to kind of stretch. And if you imagine a molecular bond looking kind of like a spring here, just imagine it vibrating and stretching and kind of going in and out like so. The way it works in IR spectroscopy is when a photon gets absorbed by a molecule, this leads to molecular vibrations, leads to longer bond length. So the more vibrational energy you have a larger average increase in bond length of the molecule. So this is a diagram showing the energy changes. So let's call this vibrational state energy. And here we have a molecule. Here it is our molecule of interest. And as this energy increases here, this jump from one energy state to the next level, this is a delta E. So when you have a greater vibrational energy, this leads to a greater average bond length here. And this here is the ground state, here's the excited state of the molecule. And this delta E, this energy that it takes to jump from the ground state to the excited state, is equal to the energy of the photon that gets absorbed by the molecule originally. So this is the basis behind how IR spectroscopy works. And we basically try to determine the molecular structure by identifying these functional groups and how they vibrate. And it shows up in something called an IR spectrum. So this is an example of what an IR spectrum can look like. It shows a lot of peaks, and these peaks represent peaks of absorption of these photon energies. So if we were to label this axis right here, this at the bottom is called the stretching frequency, whereas the y-axis is the number of photons absorbed. So I'm going to write that really quick. All right, and a good thing to know about peaks within the IR spectrum has to do with the intensities of the peaks, whether it's really, deep, kind of going down towards the bottom versus something like weak, which doesn't really have much substance or depth here. So that has to do with the polarity of the bond in our molecule. So if you take something like HCl, for example, it has a pretty strong dipole moment due to the fact that the chlorine is a lot more electronegative than the hydrogen. So if you remember electronegativity, the electrons get pulled over to the chlorine here. And that's where this delta minus comes from. And an important concept to know is that the greater bond dipole that you have, the greater the absorption, and then the stronger the peak. So if you're looking at an IR spectrum, something like this, which is considered a pretty strong peak, especially this one right here, this represents a pretty strong bond dipole relative to something like this, which is a little bit weaker. So this represents a weaker bond dipole. So there are 5 major zones that compose the IR spectrum. I'm not going to read all of them out for you, but if you just take a look at your IR spectrum, I kind of have them outlined here. There's zone 1, zone 2, zone 3, zone 4, and zone 5. And actually anything over here beyond these zones is considered the fingerprint region. And for our purposes, it's not really that important for our classes. But just know this is what goes over on the side beyond like the 5 major zones that we're considering. So this is really where our focus is, and it's important to understand what the ranges of the zones are so you can kind of remember what you should be looking for in each of these zones. So know what functional groups roughly go in each zone, and also know the ranges of the zones. This is going to really give you a very quick and easy way to analyze the IR spectrum. But I know for most UCLA classes, they will provide you with a chart that has the information about what the specific functional groups are and what their specific ranges are within the IR spectrum. All right, so here I have an image of an IR spectrum as well as a molecule. This is 2-methylpropanol. And we're going to work backwards here basically and try to look at the IR spectrum of 2-methylpropanol and identify what functional groups we see in its IR spectrum and confirm it in the image of the molecular structure. Now, this is not exactly the type of practice problem you might have on an exam, for example, but this is a good way for us to learn how to identify functional groups in the IR spectrum and kind of understand the thought process that we should go through when we're trying to identify the molecular structure of our unknown substance. So let's take a look at zone 1 here. And zone 1 is, if you look just within these bars, there's not really anything of value here. There's just kind of not really any peaks, maybe a little bit of shakiness, but no peaks here. So anything in zone 1 that's indicated in our charts would indicate that there's nothing there. And I'm just right now looking at a chart that has the functional group name, the bonds, the stretching frequency, and the intensity, whether it's strong or weak. You can have, I'm sure your professor will provide you something like that to look at as well for the exam, or you can look at something online. So let's take a look at zone 2 now. So zone 2, I can see that there's a lot of things going on with these peaks here. So the first thing that really stands out to me is the relatively strong peaks that I see around here and right around here. So I'm going to try my best to indicate these. But this is this peak at approximately 2900, and here's another peak at approximately 2700. And if you look at your handy dandy chart with the functional groups and their stretching frequencies, you can see that these bands at 2900 and 2700 are representing the aldehyde sp2-CH bond. So that's this one right here. So here's the aldehyde, here's that CH-sp2 bond. And then something else that's good to highlight here is you notice kind of like the width of these peaks. There's a lot really going on around this region. And so this represents a region of approximately 2800, I would say, about. And when you have a lot of things going on around the 2800 to 2900 region, a lot of mini, like smaller peaks here, this usually represents something like a sp3 CH. And I'm actually going to put, this looks more like 2850-ish. So I'm going to put 2850 here. So this actually represents something more like an sp3CH, and these are where the methyl groups are. Usually these peaks aren't super helpful since a lot of molecules tend to have methyl groups or CH bonds that are not sp2. So I wouldn't use this as like a super definitive indicator of what's in the molecule, but it's good to kind of keep an eye out for those so you can see what you're looking at. Let's move on to zone 3 now. So there's no peaks here, I can see that. So I'm going to move on to zone 4. So zone 4 has a very, very strong peak here. So this is actually indicative of around 1700, 15, 16, 17. I'm actually going to go 1740 here. It looks like it's a little bit more in the middle. So this actually represents an aldehyde ketone, or aldehyde carbonyl. So this is this bond right here, as indicating with this very strong peak. And usually if you see a very, very strong peak around the 1700 region, that usually indicates that the molecule has some type of carbonyl in it, a C double bonded to an O. All right, let's look at zone 5 now. So zone 5 has a peak around, let's see, 1450. There's really nothing too strong to highlight here. There is a strong peak here, but nothing relevant into the molecule. So something to keep in mind with this This is also kind of going into our fingerprint region here. So something to keep in mind with the IR spectrum is that there's always a lot of random peaks and things going on. So you just have to really learn how to focus on which ones are the major ones that we're looking at. So the only thing that we could consider maybe seeing in zone 5 is either an alkene or a benzene, but those are a little bit more distinctive. Besides, an alkene would be in the 1600 region, which is not where we are at. So nothing of value here. So we're going to move on to the next point. So just some random tips that I usually find very helpful. In terms of looking for absorption peaks, I tend to, in my head, do a preliminary assessment looking at the IR spectrum of what I can see. And what I usually look for first is some kind of ketone or carbonyl. And this is usually around the 1700 region. The next thing I look for is an alcohol. And an alcohol is usually a very broad and strong peak around 3600, 3200. It's in a pretty broad range, but you see it's just a very wide peak in around the 3200 to 3600. And the last thing that's really helpful to see is the benzene ring, and the benzene ring is in zone 5 with its C double bonded to a C, the alkene, but the benzene alkene specifically. And this is approximately something at 1600, but also around 1500. Just write that here. And I actually have an indication of a molecule called toluene here. And this is what toluene looks like. You see there's that benzene ring with the methyl group attached. And something really distinctive about a benzene or a molecule with a benzene in it is this aromatic region here. It's kind of due to these overtones when the photon gets absorbed. So you don't really need to know the basics for what causes this, but just know you see kind of like this interesting series of four peaks right around the 1600, 1800 region. And you can also see pretty strong peaks in these fingerprint regions, like kind of going into there. Those are just some quick tips. They're not going to tell you exactly what the molecule looks like, but these are some ways that I try to streamline the process. All right, so thanks for listening.